So these ones are just kind of to jog our memory about how differentiating something with a different base works. So just like the derivative of e to the stuff is e to the stuff times the derivative of the stuff, the derivative of 4 to the stuff is 4 to the stuff x cubed plus sine of 2x times the derivative of the stuff, which is 3x squared plus the derivative of sine of 2x is cosine of 2x times 2, right? Because you have to multiply the derivative of 2x. And then we also have to multiply the natural log of our base, which is the natural log of 4. That's how we take the derivative of this. In fact, I should ask you guys. No, I shouldn't ask you guys. This is really not the place to do it. I will just mention again, right? Alternatively, your professor might encourage you to rewrite the function as e to the natural log of 4 to the stuff and then bring down the stuff in front of the natural log and rewrite it as e to the x cubed plus sine of 2x all times natural log of 4, and then differentiate it that way. That is also a valid way to do it, but I will tell you, at least for the ones where the base is constant, like 4 or 5 or 7 or whatever, I think it's easier just to kind of memorize this formula. The derivative of a constant to the stuff is the same constant to the stuff times the derivative of the stuff times the natural log of the base. Now, I think it's easier that way, but I can also understand that if your teacher wants you to maybe show more work, this is a process where you actually do show more work. So why are we putting the natural log? So that's a good question, Lauren. So why would you do it this way? Well, because we know, so let's pretend like we forgot that when you do the derivative of 4 to the stuff, you get 4 to the stuff times the derivative of the stuff times the natural log of 4. Well, you can rewrite anything as e to the natural log of that thing. So just in general, right? If you have a thing, right, it's kind of dumb, but if you have something, it is always equal to e to the natural log of that thing, right? X equals e to the natural log of x. G of x equals e to the natural log of g of x. So but the reason we're doing that is because we're pretending like we know how to differentiate e to the stuff and don't know how to differentiate 4 to the stuff. So we don't know how to do this, but we're like, oh yeah, I know how to differentiate e to a thing. The derivative of e to a thing is e to the thing times the derivative of that thing. So we can rewrite it this way, first as e to the natural log of 4 to the x cubed plus sine of 2x, which is the same as 4 to the x cubed plus sine of 2x, and then bring that power down in front because of the logarithm rules. So if you have the natural log of something to a power, that power gets to come down in front of the natural log. And then we can use the rule for differentiating e to a thing. So here's the rest of the work. The derivative of e to the stuff is the same e to the stuff, e to the x cubed plus sine of 2x times the natural log of 4 times the derivative of that stuff. So the derivative of that stuff is, well, check it out. We have some variable thing times a constant. When you take the derivative of a variable times a constant, you just leave the constant multiple. So you're going to get the derivative of this stuff here, which is going to be your 3x squared plus cosine of 2x times 2, and then times that constant multiple. But look, this is exactly the same as this. It just looks a little different. I've got this part here is the same as this part here, right? E to the this times natural log of 4 is really e to the natural log of 4 to the stuff, which is really the same as that. And then you've got the same 3x squared plus cosine of 2x times 2, 3x squared plus cosine of 2x times 2, and the same natural log of 4. Just to clarify, the rule used to solve this problem was the derivative. Except so you're missing. So Marshall, sorry, not to call you out. I mean, it's fine. I apologize. I try to, when people write me private messages, I try not to say their names because maybe they don't want them to know. Sorry. Anyway, Yes, when you take the derivative of, yeah, that's the rule I was using. So there's basically two ways to take the derivative of a of the stuff. Yeah, so if you want to take the derivative of a to the stuff, you can either, well, actually, there's technically three ways you can do it. One way is to memorize the formula. The derivative of a to the stuff is a to the stuff times the derivative of the stuff times the natural log of a. Let me see what you guys see. Yeah, totally. Another way you can do it is say, well, the derivative of a to the stuff is the same as the derivative of e to the natural log of a to the stuff, which is the same as the derivative of e to the stuff times natural log of a, which is equal to, now we can differentiate, and we know the derivative of e to the thing, right? The derivative of e to the thing is e to the same thing, which, oh, sorry, times the derivative of that thing up there. But the derivative of a function times a constant is just the derivative of that function times that constant. But then e to the stuff times the natural log of a is really the same as e to the natural log of a to the stuff, which is really the same as a to the stuff. So this is really equal to a to the stuff times the derivative of the stuff times the natural log of a. So that's what I'm saying. You can either memorize it, but if someone wanted you to show more work, this is work you could show. There is a third way you could do it using implicit differentiation, which we've talked about before, but I don't think we need to say a third way to do it, unless you guys really want to. So that's how this one works. Let's look at the other one. I'm going to take the derivative of log base 6 of x to the 7th minus tangent of x. So I know the derivative. So when I hear log, whether it's natural log, log base 6, log base 10, log base anything, when I'm thinking the derivative of log, I don't care what the base is, I know whenever I'm taking the derivative of log of a thing, or the log of some stuff, I'm always going to get 1 over the stuff times the derivative of stuff. And then maybe I have to deal with the base after that. So I know my derivative is going to be 1 over x to the 7th minus tangent of x times the derivative of x to the 7th minus tangent of x, which is 7x to the 6th minus secant squared of x. And then I also, now I think about the base. I'm like, oh, there's a base that's not the natural base e. The base is 6. I need to divide by the natural log of that base. So when your base isn't e in an exponential function, we always end up multiplying by the natural log of that base. In a logarithmic function, we always end up dividing by the natural log of that base. Always, always, always. Let's do a couple more just to make sure everyone is super duper extra cool with this. Let's say I want to find the derivative of 5 to the, let's make it real fun. Let's make it 5 to the, I'll make it super duper terrible. Yeah, fine, why not? 5 to the x over x squared plus 1. Seems kind of gross. So we are going to have to use the quotient rule here. So the derivative is going to be, so again, I'm just using the rule. I've got 5 to the stuff. My derivative is 5 to the stuff times the derivative of the stuff times the natural log of 5. So it's going to be 5 to the x over x squared plus 1. Maybe I don't want to take that derivative right now. I'm just going to write this instead. I'm going to write the derivative of x over x squared plus 1. Like that. Which means I'm going to have to write another step. That's okay. Times the natural log of 5. One advantage to doing this is that if you actually do it like this, and maybe you screw up the derivative of that somehow, someone can still see that you at least knew what you were doing, right? Like maybe, because what I'm trying to say is, like, what if we screwed up this derivative really bad and it kind of looked super wrong? If you write this stuff before it, the person reading your work is like, well, I can see that they have the right idea. They know the derivative is 5 of this stuff times the derivative of stuff times natural log of 5. They've got the idea of this stuff. So sometimes it's good to show more work. A lot of times it's good to show more work. So this is going to be 5 to the x over x squared plus 1. Differentiate this using the quotient rule. So it's going to be the bottom x squared plus 1 times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 2x, all over the bottom squared, all times the natural log. And if they didn't say to simplify it, I would just leave it like that. If they did say to simplify it, I would simplify this just a little bit. I've got 5 to the x over x squared plus 1. Here I've got x squared plus 1 minus 2x squared. That's going to be a negative x squared plus 1, or I prefer to write 1 minus x squared over x squared plus 1 squared times the natural log of 5. That's how I would prefer to write this answer. Let's look at another logarithm one too. So I'm going to have an added kind of extra piece here. So let's say I want to find the derivative of the log base 2 of, what have I got here? Sure, let's do it this way. Let's say x to the 7th times e to the x times secant to the 6th of x. You might say to yourself, well, James, that looks terrible. I don't want to do 1 over the stuff times the derivative of that stuff, because the derivative of that I had to use like the triple product rule, which is kind of terrible. In case you don't know, right, the triple product rule, or really the product of any number of things, not that you really have to do that, but if you're trying to find the derivative of, like, say, f times g times h, where all those are functions of x, you get each derivative times the rest of the not derivatives. So you get f prime times g times h plus f times g prime times h plus f g times h prime. And that's true no matter how many things you multiply together. So if it was a product of 4 things you want to take the derivative of, you would get 4 pieces. You would get first derivative times the other 3 pieces, second derivative times the other 3 pieces, third derivative times the other 3 pieces, fourth derivative times the other 3 pieces. That's a good question, Marshall. I don't think so. I mean, not that you couldn't have a situation where the base of the log is variable, but it's definitely not something that we really encounter. Yeah, let's maybe after we do this question, we can explore that for just 1 second and think about it. Yeah, but I mean, to answer your question, you're not going to see that. I'm trying to think, like, if you had like y equal to, well, here, so actually we do encounter it kind of all the time. We just don't really think about it. So if you had y equal to log base x of 2, well, maybe not. Maybe I'm saying crazy things here. You could rewrite that as x to the y equal. No, that seems kind of funky. Yeah, I don't think we encountered this really ever, because yeah, I mean, not that you couldn't graph that, but it would be weird. Yeah, sorry, I'm getting off on a tangent here. This is not important. You're never going to see this. I shouldn't say it. It's not that it's not important. It's just that you're never going to see it. It could be super important. Maybe you really found something. I don't know. Anyway, back to this. The point of this is I would really rather prefer to not use the triple product rule, and I don't have to. If you have a log of a product or quotient, you can break it up into many logs. Notice that when I rewrite this, I'm not differentiating yet. I'm just simplifying. Since I'm not differentiating yet, I'm still going to write the thing that indicates that I have to take the derivative. So this is equal to the derivative of log base 2 of x to the 7th plus log base 2 of e to the x plus log base 2 of secant to the 6th x. And now, again, before I differentiate, I'm going to simplify even further. I'm going to bring this power of 7 down. I'm going to bring this power of x down. I'm going to bring this power of 6 down. Right? Because that is secant of x to the 6th power. So that's 6 times log base 2 of secant of x. And now we can finally differentiate. So I'm going to get 7 times the derivative of log base 2 of x is 1 over x, and then I just have to divide by the natural log of 2. This one's a little bit more interesting. So this one is x times a constant, right? Log base 2 of e is just a number. I don't know what it is, but it's just a number. So that's going to be 1 times log base 2. Kind of funky. That's all right. Plus 6 times the derivative of log base 2 of secant of x is going to be 1 over secant of x times the derivative of secant of x, which is secant of x times tangent of x. Let's go ahead and write that on the top, so we don't run out of room here. And then we also have to divide by the natural log of 2. You will notice, hopefully here, that you could cancel out a secant. So if you really wanted to write this a little bit more simply, you could write it as 7 over x natural log of 2 plus log base 2 of e plus 6 tangent of x over the natural log of 2. Yeah. Let's see here. So let's go ahead and talk about logarithmic differentiation. So we actually used it already, right? When we first differentiated like 5 to the x, we took the natural log of both sides. Oh, sure, yeah. We took the natural log of both sides. We differentiated both sides using implicit on the left. We're going to use that same process for differentiating things where the base and the exponent both have variables. You're welcome. And kind of the classic example of this is differentiating x to the x. We're going to do a number of examples. We're going to see that they all play out the same way. And again, so I should ask you guys, are your professors, so first of all, have you seen an example like this yet in your class? And it might, I know there's some in your homework. Like I've definitely seen homework problems that are like find the derivative of like 8x to the 2x or something like that. But have you guys seen problems like this shown to you by your instructors? Yes? No? Maybe? Okay. Okay. So I will show you, I'll show you both ways of doing it. Because there are 2 valid ways of doing this. So here's the way I would do it. I would write it as y equal to the natural log of x to the x. Sorry, whoa, not yet. Not the natural log yet. Sorry. I would write it as y equal to x to the x. And then I would take the natural log of both sides. So I really want to stress here, you cannot use the power rule, right? You can't just say that y prime is x times x to the x minus 1. That is not true. So whenever you have a variable in your base and your exponents, you really have to do something a little bit more complicated. So the natural log of y equals the natural log of x to the x. And the reason we're taking the natural log of both sides is so that we can get this variable out of the exponent. We can bring that down in front. So the natural log of y equals x times natural log of x. Then we're going to differentiate both sides. Remembering that y is in fact a function of x, the derivative of the natural log of y, or the natural log of some stuff, is 1 over the stuff times the derivative of the stuff. It's always what we're going to get when we differentiate the natural log of y, if we're assuming that y is a function of x, which we always are in this class. Or at least almost always are. On the other side, we have to use the product rule because we have a variable times another variable. So it's going to be the derivative of the first part times the second part plus the first part times the derivative of the second part. So 1 times natural log of x plus x times 1 over x. Now we're going to solve for y prime, and we're also going to simplify the right-hand side. So multiply both sides by y. So y prime equals y times natural log of x plus x times 1 over x is 1. And then finally, we replace y with what it's equal to. So their answer is also a function of x. So y prime is x to the x times the natural log of x plus 1. And that's the process of logarithmic differentiation. You take the natural log of both sides, you bring down your power, you differentiate both sides. The left side is always going to be 1 over y prime. The right side, you're always going to have to use like the product of the quotient rule, because you're always going to have something with x times something with x. And maybe this is like 1 over x, so you can write it as a quotient, but some sort of product or quotient rule. Then after you do that, you will multiply both sides by y and then replace y with what it's equal to. Usually these last two steps, you can kind of just make it one step. Like, oh, I'm going to multiply by y and also replace it at the same time to get this, but it's also fine to write out the steps. Okay. The other thing you can do, let's actually do another example of this, and then we'll go back and we'll show how you can do them both using a different method. So let's say we have, y equal to sine of x to the x squared. And so just as kind of a point of interest, or maybe not interest, but just so everyone knows, when you have like powers within powers, if there are no parentheses, you always kind of assume the parentheses start as high as possible. So like if someone said you had something silly like y equal to x to the 3x, I don't want that because that's required parentheses. Let's say I had x to the x to the x to the x, right? Super dumb looking. What that means is, or even, or 2 to the third to the fourth to the fifth. You can't make any assumptions. You have, well, I guess that's not true. You have to make assumptions. You have to assume that the parentheses work like this. So first you do x to the x, then you do x to the that, then you do x to the that. And it does matter, right? 3 to the 3 to the 3 is different than 3 to the 3 to the 3. This here is that. That's, let's see, 3 to the third is 27. Where here, 3 to the third is 27. 3 to the 27th is a very different number than 27 to the third. Another way you can think about this one is here, since you have a power to a power, that power can multiply, and you get 3 to the 9th, which is definitely not the same as 3 to the 27th. So when you have something like this, you can't bring that power down like you often would, or multiply powers when you have something like that. So just be extra, extra careful. And again, right, if no one has written any parentheses, you have to assume the parentheses are kind of as high as possible. Okay, enough about that. Don't super stress about that. It doesn't come up a lot, but it does occasionally come like, oh, when I've got like x to the x to the x, it's really x to the x to the x. All right, back to this. So what I'm saying here, right, is this is not the same as sine of x to the x quantity squared, right? These are different things. Okay, let's go ahead and differentiate. So we're going to take the natural log of both sides. And then we're going to bring down that power. So we're going to get the natural log of y equal to x squared times the natural log of sine of x. And then we're going to differentiate both sides. The derivative of the natural log of y is 1 over y times y prime. The derivative of the right side, I'm going to have to use the product rule. Derivative of x squared is 2x times, leave the natural log of sine of x alone, plus x squared times the derivative of the natural log of sine of x is 1 over sine of x times the derivative of sine of x, which is cosine of x. some of this, kind of in the way. And then we're going to multiply both sides by y. So y prime equals y times all of this. And so we're going to simplify just a tiny bit. You don't really need to. There's one thing I like to do because it's just simple. Cosine of x divided by sine of x is cotangent of x. So I'm going to write this as x squared times cotangent of x. And then finally, I'm going to replace y with y is equal to. So I get y prime equal to sine of x to the x squared. Right, that's what this is right here. Sine of x to the x squared times all that. 2x times natural log of sine of x plus x squared cotangent of x. I don't know, that's like in parentheses. Cool. Okay. So this is how I personally would recommend doing it. I like this process. It's straightforward. Also, just in general, this idea of logarithmic differentiation, where we take the natural log of both sides and then do some stuff, is a process that we use not infrequently. For example, some textbooks, I don't know if yours does or not, some textbooks give you like super crazy looking, maybe not super crazy, but a textbook could give you a function like this, like y equal to x cubed times sine of x over the square root of x to the fourth plus 1. And although you could differentiate that directly, it's kind of gross, right? You have to do the quotient rule, the product rule, yeah. You could use logarithmic differentiation for this and say, oh, I'm going to take the natural log of both sides. The natural log of y equals the natural log of all this stuff. And then break this right side up using the rules of logarithms. So you can break this up as the natural log of y equals, I'm going to do it fast. So it's going to be the natural log of x cubed plus the natural log of sine of x minus the natural log of the square root of x to the fourth plus 1. And then those powers come down. So it's really 3 natural log of x plus the natural log of sine of x minus the power for the square root is 1/2 the natural log of x to the fourth plus 1. And then you can take the derivative of both sides. So you get 1 over y prime equal to 3 times 1 over x plus the derivative of the natural log of sine is 1 over sine times cosine, which is cotangent of x. And then the derivative of this is going to be, let's see, 1 over 2 times 1 over x to the fourth plus 1 times the derivative of x to the fourth plus 1, which is 4x cubed. And then you can multiply by y, which is just all this grossness. So it's x cubed times the sine of x over the square root of x to the fourth plus 1 times all that stuff right there. So that's an example of logarithmic differentiation also. It's the same process, right? You took the log of both sides. On this one, well, I guess we do here, right? You take the log of both sides, you simplify the right-hand side, and then you differentiate both sides, and then you multiply by y. It's just this is not super necessary to use it, whereas this kind of is. Okay, I know I mentioned that there is another way to do these problems. Let's go ahead and go over that as well. So you can do it this way, and I would recommend doing it this way. I think this is the nicer, more, I don't know. To me, it feels more thoughtful. That doesn't mean it's right. It is right, but it doesn't mean it's the only way it's right. So another way to do this is to do the thing we've been doing for other stuff. Right? I'm going to rewrite x to the x as e to the natural log of x to the x. And then I'm going to rewrite that as e to the x times the natural log of x. So then if I'm going to differentiate x to the x, I can think of it as differentiating e to the x times natural log of x. And then the derivative of that is going to be, well, I know how to find the derivative of e to the stuff. That's going to be e to the stuff times the derivative of that stuff. Notice in both of these problems, I'm going to be taking the derivative of x times natural log of x, either way, right? Whether it shows up here, whether it shows up here. Oh, you're always doing the same work, just maybe in a different kind of order. So then I get e to the x times natural log of x. And I know the derivative of x times natural log of x, I have to use the product rule. I get 1 times natural log of x plus x times the derivative of natural log of x, which is 1 over x. So then I'm going to rewrite this. Now, here's the thing. People don't usually leave this way, because we know that e to the x, well, first of all, the thing I really think of is that I know when I differentiate something like this, where you've got a variable in the exponent, the same thing always reoccurs. You always get that same expression back. And not getting it back feels wrong to me. So I really want to be like, oh yeah, I know that e to the x times natural log of x is really e to the natural log of x to the x, which is really equal to x to the x. So I really think you should replace that with x to the x. Also, most of the time people write the answers, it's going to look like that. And then times natural log of x plus x times 1 over x is 1. Is this better? Who knows? It might feel better just because you don't have to do this thing where you set y equal to your function, take the natural log of both sides, right? It is something you have to remember to do if you're doing it this way. You have to say that, oh, I'm trying to take the derivative of this thing. I want to use logarithmic differentiation. I have to say y equals my function, and then take the natural log of both sides. And then differentiate both sides using implicit differentiation after you simplify this. Either way is perfectly fine. I don't know if your professor is going to want you to do it one way or the other. What I'll say about this is, as far as your graded work, I imagine there'll be maybe 1 or 2, I don't know if you guys are doing exams or quizzes or whatever, but usually when I was teaching a class like this, I would maybe ask 1 question like this on a midterm exam and 1 question like this on a final. So there's not a lot of graded work that your teacher is going to be seeing, right? Because all the homework problems, they don't grade those. So I don't know how they want you to do it, but you can do it either way. And both ways work. In fact, we can even go back to this other problem here, this sine of x to the x squared one. We can do that one that way as well. So instead, sure, we can say, oh, I want to find the derivative of e to the natural log of sine of x to the x squared, which is equal to e to the x squared times natural log of sine of x. And again, we know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So my y prime here is going to be e to the stuff times the derivative of that, which I'm going to use the product rule for. So it's going to be 2x times natural log of sine of x plus x squared times 1 over sine of x times cosine of x is cotangent. I can start that way. Cosine of x over sine of x. And then e to the x squared times natural log of sine of x is that, which is that. So I end up getting sine of x to the x squared times this hot mess over here. 2x natural log of sine of x plus x squared times cotangent of x. Same answer. Upon reflection, even though I prefer this because I think it makes you, I don't know, maybe not. I feel like they both make you think. This way certainly does seem to be a little bit more compact, right? There's not quite as many steps to this process, it feels like. So if I had to pick one for the amount of work I had to write down, I would probably pick doing it this way because it feels like just a little bit less writing down stuff. But really, you should do whatever works best for you, right? If you're like, James, this totally makes sense, I'm gonna do it that way, great. If you're like, James, that way sucks, I'm gonna do it that way, also great. They're both great because they're both right. Yeah. Okay, so what time is it? Oh, we got plenty of time, great. Let me take a look here. I know someone asked me a specific homework question that I wanted to make sure I got to. Also, if you ever have questions about the quiz that you want me to do in class, I'm also happy to do that. The quiz, specifically the quiz I do, or really, you know, anything, as long as it's not like, right? I'm happy to look at homework problems. Your exam stuff, obviously, I should not be helping you with, but you guys already knew that. So here is the question that was asked. Find the derivative of, now I will say the way this is written is a little bit suggestive, just a little bit. So it says find the derivative of y equal to 9 to the x to the 2 to the x power. And what do I mean by this is a little suggestive? Well, whenever I was writing an exam and I knew I wanted my students to use logarithmic differentiation, meaning you take the natural log of both sides, I would usually try and write it as y equal to the thing to make it easier for them to see that, oh, I can just take the natural log of both sides. I will also do this one both ways because, again, I think it's good to see both ways. Unless you guys are sick of seeing it both ways, right? If you just want me to do it one way, I can also do that. But I think both ways is probably good. Okay, so I'm going to do it the way definitely both ways. Awesome, cool. So the natural log of y equals the natural log of 9 to the x to the 2 to the x. Now this is a little bit super funky. Let's actually, I'm going to show you guys a few things here. So I'm going to bring down my power. So this is equal to 2 to the x times the natural log of 9 to the x. But then I can also bring down the x. So it's really x times 2 to the x times the natural log of 9. Another way to see this, just so you guys know, is that if you have a power to a power, you can multiply those powers, right? So I know before I was saying, like, you have to be careful about that. Well, right, if you have, if you, like before, I said, if you have 3 to the 3 to 3 like that, you can totally multiply those powers and get 3 to the 9. Whereas it's not if you have that. So those parentheses there kind of help us out. You could also write this as 9 to the x times 2 to the x. And so then when you take the natural log of both sides, you get the natural log of y equal to the natural log of 9 to the x times 2 to the x, which totally gets us to x times 2 to the x times natural log of 9. So either way is correct. I mean, really, it's the same work, just a different way of thinking about it. So, So here's what we've got. We've got the natural log of y equal to x times 2 to the x times the natural log of 9. I don't want to do that. So I'm just going to take the derivative. So derivative of the natural log of y is 1 over y times y prime. The right-hand side, I'm going to have to use the product rule. So I would maybe encourage everybody to think of this as the constant natural log of 9, which is just going to hang out because it's a constant multiple, times the product x times 2 to the x. Great, so my derivative of that, constant multiples hang out. Derivatives of constants are just 0. But when it's a constant times a function, it just sticks around. Can't get rid of it. But then the derivative of x times 2 to the x, we're going to use the product rule. So the derivative of x is 1 times leave 2 to the x alone, plus now we flip it. We leave x alone. And what's the derivative of 2 to the x? It's the one we should know. Anyone want to write it in the chat? You're like, damn, I forgot that one. So derivative of 2 to the x is 2 to the x times natural log of 2. We're going to solve for y prime. So I'm going to do this next step, since I'm out of room on the bottom here, I'm going to do the next part that would usually be 2 steps as 1 step. So I'm going to multiply both sides by y. I'm also going to replace y with what it's actually equal to. So I'm going to get y prime equal to y, right, which is 9 to the x to the 2 to the x, times all this natural log of 9 times 2 to the x plus x times 2 to the x times natural log of 2. It's a little bit more easy to see. Right, and again, just to make sure everyone's super clear with this, that's your y. So I multiply both sides by y, I got y prime equal to y times all that jazz, and then we replace y with what it's actually equal to. So kind of gnarly. just as mentioned here, if you were asked to simplify this, the only simplification I really see as being necessary is you could factor out the 2 to the x from inside this parentheses and write it as 9 to the x to the 2 to the x times the natural log of 9 times 2 to the x times 1 plus x natural log of 2. But I don't really think that's probably necessary. All right, let's do it the other way. And I think after this section, we're then moving towards talking about antiderivatives. I think this is kind of the, so I should, oh, actually, I should, yeah, the problem is a little aggressive for sure. Let me look at one thing real quick. I just want to double check something for my own personal knowledge here. See chapter 4. I know this is an old. Yeah, do we not talk about that? Interesting. Logarithmic, exponential. Okay, yeah. So I was about to say something that's slightly wrong. I would say after this chapter, we know how to differentiate just about every kind of function there is. That is true with kind of one exception, which is the inverse trig functions, which I don't actually know if we cover in this class or not. So let me see here. Trig functions. Yeah, I think we might not do derivatives of inverse trig functions, which is perfectly fine. You're not missing out. But yeah. So after this section, we will, here's what I'll say. After the section, we should know how to differentiate everything that we will be expected to differentiate in this class. So as far as we're concerned, once we're done with this, we pretty much know how to take the derivative of any function that we are going to be asked to take the derivative of. Yeah, I also agree. The problem is gnarly. So let's see, let's do it again, just because it's so much fun. So we've got the derivative of 9 to the x to the 2 to the x, which we're going to rewrite as the derivative of e to the natural log of the same thing. Feels dumb already. So then we're going to bring down the 2 to the x. So it's going to be the derivative of e to the 2 to the x times the natural log of 9 to the x. And I will mention here, you technically don't have to bring down this x, right? We are capable of differentiating the natural log of 9 to the x. It'd be 1 over 9 to the x times the derivative of 9 to the x, which is 9 to the x times the natural log of 9. But I think it's easier to bring it down. So I'm going to rewrite this as the derivative of e to the x times 2 to the x times natural log of 9. And notice, once again, we differentiate this thing. We're going to be differentiating the derivative of e to the stuff is e to the stuff times the derivative of that stuff. We're going to be taking the derivative of x times 2 to the x times natural log of 9, just like we had to take the derivative of x times 2 to the x times natural log of 9. Right? You're always going to be having to take that same derivative either way. It just kind of depends where it's going to show up. So we know that the derivative of e to the stuff is the same e to the stuff times, good God, times, where's the other eraser going? I'm hiding my erasers from myself. The derivative of that stuff. Okay, so I've got a constant times a product. So the constant multiple hangs out, and the derivative of that product, we're going to use the product rule just like we did on the other side of the board. It's going to be 1 times 2 to the x, right? The derivative of x times 2 to the x plus x times the derivative of 2 to the x, which is 2 to the x times the natural log of 2. And then finally, we should rewrite this as that, right? These are the same thing. It probably wouldn't, like, I don't think you would lose points for writing it that way. I don't think, because it's technically the same thing and correct. But it is very much standard practice to rewrite this as the function you started with, because that's what it is. I should say rewrite it so that it looks the same as the function started with. So it's 9 to the x times to the 2 to the x times the natural log of 9 times 2 to the x plus x times 2 to the x times natural log of 2. Gross, but the same. I suppose from my perspective, I think this method maybe is a smidge easier to get the final answer in the right looking way, because when you're doing this thing where you're multiplying by y and then replacing what y with what it's equal to, it's very obvious. Oh, well, y is the thing I said y was equal to, so that's just going to go in there. Whereas doing it this other way, it's not always as easy or memorable to be like, oh yeah, I should replace that gross looking thing with the slightly less gross looking thing we started with, because that's what it is, and we started with that, so we should really use that. I wouldn't stress too much about those. So you should pick for yourself which way you want to do it and just do it that way. And I really would kind of recommend picking one or the other so that you get very good at doing it the way that you're going to do it, because you shouldn't have to do it both ways. Again, this method of differentiating where you take the natural log of both sides is called logarithmic differentiation, and it is applicable to non-exponential functions, right? Like I showed that kind of a quick example on the side of here. You could totally use it to take the derivative of some gross looking quotient, where you wouldn't really write it. I mean, I guess you could, but you wouldn't really write it as e to the natural log of that gross looking quotient. It would actually totally work the same kind of way. It's just, I guess it's always true, right? If you're going to take the derivative of something and you see that taking the natural log of both sides would be beneficial, another alternate method of going is saying, oh, I'm just going to call my thing e to the natural log of that thing and take the derivative that way. And that also totally works. So either way is good. Either way will work. Do what you want to do. Do what feels most comfortable. So let me take a look at your assignment real quick just to see if there's any other problems that really kind of stand out to me. I should look at the homework 5 for, what's his name? Ma, I think. I don't remember who's who. No, okay. Oh, that's a good one. Let's do one like that. Sure. So I see a question on homework 5 that seems good to take a look at. Homework 4 doesn't seem too terrible. All right. So, oh, I know what I was going to do. Yeah. Let's see. Yeah. I got ideas. So let's say I want to take the derivative of y equal to, let's make it x squared times, what did it have here? Sorry. That seems too easy now. That's fine. Fine, we can do an easier one. X squared times 3 to the 2x minus 1. It almost feels too easy. No, not really. It doesn't feel too easy. I'm going to do it the way I have always done it growing up when I learned calculus, right? Like growing up, I was doing these when I was like 5. No. So I'm going to take the natural log of those things. I think it's especially nice here. Well, again, I keep saying this, like, I'm still going to take the natural log of this as you break it up. But either way you do it, whether you do it this way or the other way, you're going to end up taking the natural log of this right-hand side, right? It's just the other way, you're going to write it as e to the natural log of this thing. But still, you're getting the natural log of the thing. So then the natural log of y equals, I'm going to break this apart before I start doing. So the idea here is that the reason you're taking the natural log is so you can make this look simpler. I'm going to write this as the natural log of x squared plus the natural log of 3 to the 2x minus 1. And then I'm going to bring down my powers. The natural log of y equals 2 natural log of x plus 2x minus 1 times the natural log of 3. Great. Let's differentiate both sides. 1 over y prime equals 2 times 1 over x plus, okay, here it's kind of reversed. This is the constant multiple that hangs out. This is the thing we're going to differentiate. Derivative of 2x minus 1 is just 2. All right. Looking at this, I would probably, I don't know. Maybe I would factor out a 2. I don't know. It seems kind of silly. Let's factor it out, sure. So y prime equals multiply both sides by y, factor out the 2 just for fun, and then you're left with a 1 over x plus the natural log of 3. So finally, we see that y prime is equal to y, which is this, times 2 times 1 over x plus natural log of 3. Again, just as a reminder, that's your y. Okay. So what I really want to emphasize about any of these problems is, or at least I should say really any of these kinds of problems, is although there's technically some super bizarre formula you can memorize, you shouldn't. You should use this process where either process, right, where you either rewrite it as e to the natural log of your stuff and simplify that way, or you take the natural log of both sides and you simplify the answer that way. Either way, you're going to be dealing with the natural log of this expression and trying to make it look nicer by using the rules of logarithms. Almost, I was going to say almost exclusively the power rule where you bring down the power, but in this example over here, we also use the prime rule. So really kind of all the rules of logarithms. Right, what else have we got here? We can do more of this, but if you guys have other questions, I'm also happy to address kind of other topics. I mean, I like talking about this, don't get me wrong, I think this is great. I'm just trying to see if there's kind of anything else that looks super gross. Let me make something up that will be kind of fun. Fun. He says fun. Let's find the following. Let's find the equation of the line tangent to f of x equal to, let's make it kind of saucy. Let's say it's 2x plus 1 to the x plus 3 power. That's going to get stupid. That's all right. It'll be fine. At x equals 1. Cool. We can do this. Yeah, this won't be too awful. Okay. Right. So let's see. Let me see. Number 16. Oh yeah, 16. 16 is not quite as bad as the one we just did, but we can go over one like that, sure. Well, let's do this one. So this is also kind of similar, but not exactly. So to find the equation of the tangent line, we need 2 pieces of information. We need a slope, meaning we need to find the derivative and then plug in that value. So we're going to find f prime of x, and then our slope is going to be f prime of 1. We have to find the derivative before we plug in the 1. And then we also need the point. The point is going to be 1 comma f of 1, right? The x comma y value. So we can actually do that right now. That's going to be 1 comma, so if I plug in 1, I get 2, 10 plus 1 is 3 to the 4th power, which is 81. So we've almost got the whole thing, right? We know that our equation of our line is going to be y minus 81 equal to our slope, which we haven't found yet, but we will, times x minus 1. We're just one derivative away from finding the equation of the tangent line. All right, I'll mix it up. I'll do it the other way, just to do it a different way. So let's write our function as e to the natural log of all that stuff, which is 2x plus 1 to the x plus 3. And of course, we're going to bring the x plus 3 down. So we're going to rewrite this as e to the x plus 3 times the natural log of 2x plus 1. And then we're going to differentiate. So our derivative, well, again, we're differentiating e to the stuff, and the derivative e to the stuff is always e to the stuff times the derivative stuff, right? I've only said it 1,000 times. Hopefully, right, it's like stuck in your head. Like, oh yeah, the derivative of this stuff is e to the stuff times derivative of the stuff. There's no escaping it. So the derivative of the stuff is e to the same exact stuff. I don't know, there should be x times the derivative of that stuff, which is going to require the product rule. So let's say that's going to be derivative of x plus 3 is 1 times the natural log of 2x plus 1 plus x plus 3 times the derivative of the natural log of 2x plus 1 is 1 over 2x plus 1 times the derivative of 2x plus 1, which is 2. And then since I don't actually care, but I could simplify this, maybe I should simplify it. If I normally, so I'm a little torn. Maybe I would simplify. I kind of want to replace this because here's the thing. I'm going to have to plug in 1. Plugging in 1 here, it might be a little confusing to be like, oh, I have e to the 4 times natural log of 3. That seems kind of weird. But if I replace it with what it's equal to, it might actually be easier to evaluate. So that's going to be, we know that that's our 2x plus 1 to the x plus 3 times all this stuff over here, which is the natural log of 2x plus 1 plus, I'm going to write this as 2 times x plus 3 over 2x plus 1. All right, so now let's do it up here. F prime of 1 is going to be, so plugging in 1, I'm going to get 3 to the 4th. Times plugging in 1 here, I get the natural log of 3. And plugging in 1 here, I get 2 times 4 over 2 plus 1. So 2 times 4 is 8 over 2 plus 1 is 3. And that's my really lovely looking slope. So then the equation of my tangent line would be y minus 81 equals this garbage, 3 to the 4th times natural log of 3 plus 8/3 times x minus 1. And you could massage that a little bit, and you could isolate y if you really want to. Not the worst thing I've ever seen. Although it's a pretty high bar since some pretty terrible math problems in my tenure as a math teacher. So, yeah, we can do more. Really gross. Sure, let's do one like this. Let's do something like, let's say our function is, I don't know, let's say it's 6x to the 7x. You guys should be pros at this by now, right? We've done like a million of them. Okay, so let's do it I'm just gonna go back and forth. Let's do it the logarithmic differentiation. So I'd like to rewrite, I would rather not use f of x, although we could. You could totally write the natural log of f of x equals the natural log of 6x to the 7x. I usually prefer to replace f of x with y if I'm going to be doing this, but it doesn't actually matter. It's just easier to write y than it is to write f of x. Then we're going to simplify. So the natural log of f of x equals 7x times the natural log of 6x. Speaking of which, someone the other day was asking me, like, they were supposed to like simplify some expression like this and do as many logs as possible, and they were getting stuck because they were leaving it like this, which I would too. But technically, we're not going to. But if you wanted to, you could totally break this up as the natural log of 6 plus the natural log of x. Feels kind of silly and unnecessary, but it is something that is valid. Well, let's not. Let's differentiate both sides. So differentiating both sides, we're going to get, again, the derivative of the natural log of some function is 1 over your function times the derivative of your function. And then the right-hand side, product rule, as usual, when we have a variable in our base and our exponent, right? Always going to be getting the product rule. I should make one up as a quotient rule. We'll do the next one as a quotient rule. Let's see here. Derivative of this is 7 times the natural log of 6x plus 7x times derivative of the natural log of 6x is 1 over 6x times 6. Sixes cancel. It's kind of worth noting, it's actually, I think it's kind of interesting, that the derivative of the natural log of any constant times x is always going to be 1 over x. Right? It's 1 over your constant times x times the constant, which is just 1 over x. It's always true. In fact, you can even see it by breaking this up. Right? This is equal to the derivative of the natural log of the constant plus the natural log of x. And then that's a constant. It's not a constant multiple anymore, so the derivative of that constant is just 0. And the derivative of natural log of x is 1 over x. Kind of cool. Kind of neat. Anyway, I guess that makes sense if you really think about it graphically, right? You're taking the natural log of x function and you're just adding something to it, which means you're shifting the whole graph up. But you're not actually changing the slope of the tangent lines anywhere. You're just moving the whole graph up. So the derivative is always the same. Kind of cool. Totally works. Anyway, cancel the sixes and solve for f prime of x. So f prime of x equals f of x times 7 natural log of 6x. And the x is also canceled here, so you just get plus 7. How exciting. And then finally, replace f of x with what it's equal to. You get f prime of x equal to 6x to the 7x times, you might factor out a 7 here, natural log of 6x plus 1. Probably don't need to factor out a 7, but hey, why not? Okay. Let's do one that actually has a quotient in it. That does come up every once in a while. The other weird things I could put in there. Ooh, yeah, that's not so exciting. Sure, I'm going to try and make it a little more interesting. Let's do this. I want to take the derivative of g of x equal to sine of x to the, what power should we decide? Let's do the power of, all right, sorry to come up with something. Let's do, that seems dumb, that's fine. 2 to the x over x plus 1. Seems relatively stupid as far as how dumb it's going to be and gross. Gross is better than it. It's not stupid, it's gross. Let's see. I keep going back and forth, so I did this one this way, so let's do the other one the other way. So I'm going to write this as, so I should again emphasize the difference between the two ways of doing this. One way, you're going to write your y or your function equal to whatever it's equal to, and then take the natural log of both sides and differentiate. This way, you're not writing natural log of both sides, you're just rewriting your function as e to the natural log of whatever you've got. Sine of x to the 2 to the x over x plus 1. Also, just a word of warning in general, when you've got exponential things like 2 to the x power, it can be really easy to accidentally let that x travel down and become 2 times x. It's not the same, right? We know it's totally different, but just be careful, right? It's really easy to, if you're writing fast, to accidentally write that as 2x, and then you get this totally different thing. So just be extra careful that your exponents don't become multiples. So then we're going to bring that down. So I'm going to have, well, this is going to be kind of nasty. Oh well. Sometimes that happens. We have e to the, I have 2 to the x over x plus 1 times sine of x. And before doing that, I'm actually going to write it so that it's easier to deal with. I'm going to write that as e to the 2 to the x times sine of x over x plus 1. All right, this is going to be gross. It's all right. So now our derivative, same thing, right? The derivative e to the stuff, you always get e to the stuff back. It's going to be e to the 2 to the x times sine of x over x plus 1 times the derivative of all that, which is going to be a little bit much, right? We have to use the quotient and the product rule. So quotient, It's the bottom times the derivative of the top, and the derivative of the top will require the product rule. So it's going to be the bottom. Let's just write it this way for now, times the derivative of the top, which I'm just going to write as 2 to the x times sine of x prime, and we'll do that part in the next step. And then minus the top, 2 to the x times sine of x, times the derivative of the bottom, which is just 1, lots of relief, something, and then over x plus 1 squared. Now, simplifying a bit, well, I'm still finishing, right? We didn't differentiate that part, so we're really not done. We know that e to the 2x, 2 to the x times sine of x over x plus 1 is the same as this, right? Literally the same, which is the same as this, which is the same as this. I feel like oh, you know what I did? I lost something. What did I lose? Anybody? Anybody? Anybody see what I lost? Yeah, the natural log. So this should be a natural log of sine of x here. So this should be 2 to the x times natural log of sine of x over x plus 1. So this should be the same thing. 2 to the x times natural log of sine of x. So that means, and this should be the derivative 2 to the x times natural log of sine of x. And this should be also 2 to the x times natural log of sine of x. Sorry about that. Okay. So, we were replacing this. So this is equal to this, is equal to this, is equal to this, which is equal to this. So we have our sine of x to the 2 to the x over x plus 1. How lovely. Times, we still have to finish this. So I'm going to have an x plus 1. Notice I can't cancel that with one of those because I can't factor an x plus 1 out. And then the derivative of this is going to be a little bit gross. It's going to be product rule. So the derivative of 2 to the x is 2 to the x times natural log of 2 times the natural log of sine of x. Plus, then we flip it, right? We leave the 2 to the x alone. And the derivative of the natural log of sine of x, I'm just going to take the shortcut. Say I know it's 1 over sine times the derivative of sine, which is 1 over sine times cosine, which is cotangent. Minus this, which is 2 to the x times natural log of sine of x. Whew, that was gross. Over x plus 1 squared. That seems pretty extreme. Extreme. Oh, okay. So 10, 15, 14, 10, 15, 14. I feel like we've done this one to death. So let me talk for 4 or 5 minutes about where we're going. So we've talked about all the derivatives you can talk about. I mean, all the derivatives you can talk about in the 16 series. Technically, there's a couple other ones, fine, whatever. But the place we're going is now we're going to talk about antiderivatives. And literally, if you know how to take a derivative and get an answer, you know what the antiderivative of that answer is. So I'm going to write out a very, very straightforward example. We know that, and I'm going to use words here because we don't have the symbology yet for antiderivatives, but we will. So let's say the following. The derivative of, I don't know, I'm going to pick some function. Let's say, and so there is actually some, when we talk about antiderivatives, people often use capital function letters for the antiderivative and lowercase function letters for the derivative. So the derivative of, I'm going to use capital F of x equal to, I don't know, let's pick something straightforward, like x cubed is, I'm going to say capital F prime of x, which we're going to call lowercase f of x often, which is going to be 3x squared. Okay. So then a fairly similar statement, although there's a little extra there. I'm going to say not the, because, so let me back up. When you take a derivative, you get one answer. When you find an antiderivative, there's actually multiple valid answers, but they're all pretty much the same, so don't worry about it. So I'm going to say, instead of the antiderivative, I'm say an antiderivative, because there's more than one. So an antiderivative of f of x equal to 3x squared is capital F of x equal to x cubed. That's it, right? If the derivative of something is equal to something else, the antiderivative of something else is the function that you took the derivative to get there. So derivatives and antiderivatives undo each other. So you get a derivative and then an antiderivative function, you get back to where you started. Now, I will be slightly cautious here and say that's not technically 100% true, because another antiderivative of the same function is f of x equal to x cubed plus 4. Because it still meets the requirement. The requirement of an antiderivative is that its derivative is the function you started with. Is the derivative of x cubed plus 4 equal to 3x squared? For sure. In fact, I could pick any function plus any constant you want. I could pick pi, or I could pick natural log of 2, or I could pick 10 to the 1000th power. All these things are constants, all their derivatives are 0. So the derivative of all of these 5 functions that I wrote down, each of these all have a derivative that is 3x squared plus 0 if you want. So all of these are antiderivatives of the function 3x squared. What we generally say is that the general antiderivative of f of x equal to 3x squared is capital F of x equal to x cubed plus any constant you like. All of those, we call it the family of antiderivatives of this particular function. But I really want to stress, if you know the derivative of this is equal to that, you know the antiderivative of this is equal to that plus a constant. And although this next picture I'm about to draw is fairly simple, I do think it kind of helps get the point across. This is, so if we take the derivative of capital F of x, we get the derivative, which we often call lowercase f of x. If we take the antiderivative of little f of x, we get back to the function we started with, capital F of x. And again, you can think of this being, I'm going to pick a different function. You can think of this being, I'm going to say this is, I don't know, let's say this is x to the 6th. The derivative of that is 6x to the 5th. The antiderivative of that is x to the 6th plus a constant. All right, that's all I have to say for today.